Hello, Sleepy Science subscribers. Welcome back to the channel tonight. Thank you for drifting here with me once more. Before we begin, please remember to subscribe and leave a like so that more people can soften into this calm space with us. And as always, I'm genuinely curious about where you're watching from and what time it is for you right now, so feel free to share it in the comments. Your messages float beautifully through this quiet horizon we're building together. Now, let's gently step into tonight's story. In the dim light of the universe, far beneath the surface of everything we can touch or see, lies a world so silent, so delicate, that even time seems hesitant to disturb it. This is the quantum level. The place where reality becomes soft at the edges, where particles drift between possibilities, and where the deepest laws of existence operate in a language more subtle than anything our senses can perceive. For the next while, let your thoughts slow, let the day fade, and let the calm of curiosity settle over you like gentle waves moving toward deeper calm. Because the quantum world is not loud or chaotic. It is quiet, like the soft breath of the universe as it rearranges itself moment by moment. And if you listen to it slowly, patiently, you might feel the strange comfort of its rhythm. The quantum world is made of fields, vast, invisible layers of energy that fill all of space, even the emptiest corners of the cosmic void. These fields are not static. They tremble, ripple, and shimmer with tiny vibrations, even in perfect darkness. Each vibration is a hint of life, a whisper of possibility, a particle waiting to emerge. In this quiet domain, matter is not solid, and time is not strict. Instead, particles exist as waves, spreading out, blending, overlapping, until something causes them to choose a single state. Imagine a particle, maybe an electron, floating in this vastness. It does not sit in one place. It drifts, expanding and contracting like a soft cloud suspended under dim light. It moves not because something pushes it, but because probability itself guides it. It exists in many potential locations, as if reality is deciding where to place it only at the very last moment. Before that moment, it is everywhere and nowhere, part of a gentle haze stretching through the quantum sea. And all around it, the universe continues its silent work. Tiny fluctuations rise and fall in the quantum fields, creating the subtle machinery that supports every star, every molecule, every breath taken anywhere in the cosmos, even in the cold, dark vacuum between galaxies, where absolute stillness seems possible. These fields never sleep. They ripple with faint energy, as though the universe is exhaling softly into the emptiness. In this early part of our journey, allow this idea to slow your mind. Even the emptiest space is alive, alive with motion, alive with potential, alive with the quiet pulse of reality keeping itself in balance. As galaxies perform their slow, graceful dances across the cosmic darkness, the quantum world beneath them keeps time. Not with ticking clocks, but with transitions so small they drift beneath all awareness. Yet these tiny changes shape everything. They decide when light appears, how atoms form, how stars ignite, how worlds begin. And as we float here at the edge of perception, listening to this gentle whispering of existence, a sense of calm begins to unfold. For in the smallest places, under the faintest glow, the universe reveals its true nature. Quiet, patient, rhythmic, timeless. Beneath every star, beneath every atom, beneath even the emptiest stretch of cosmic darkness, there lies a subtle network of energy known as quantum fields. These fields are not objects, not particles, not waves in the traditional sense. They are the foundational fabric of everything, spreading infinitely, filling the entire universe with a silent potential that never truly rests. Even in stillness, even in the cold void, they shimmer softly with motion. a motion so small, so delicate, that it feels less like activity and more like a whisper drifting across the edge of existence. Each type of particle we know, a photon, an electron, a quark, is not a thing on its own, but rather a tiny ripple within its corresponding field. When the field vibrates in just the right way, a particle appears. When the vibration fades, the particle disappears. What remains is the field itself, stretching across the cosmos in deeper calm. In this sense, particles are not permanent building blocks. They are temporary notes played upon an invisible instrument, rising and fading gently like soft echoes in dim light. These quantum fields do not behave like fabric in the familiar sense. They do not wrinkle, stretch, or tear. Instead, they fluctuate. Even in absolute silence, they generate fleeting disturbances. Virtual particles that emerge for the briefest moment before dissolving again. These fluctuations are tiny, far too small to observe directly, yet they shape everything that happens. They influence how atoms bind, how energy spreads, how forces interact. They are the quiet machinery hidden beneath the visible universe. Imagine standing at the edge of a quiet horizon, watching gentle waves drift toward you. Each wave rises for a moment, then softens back into the sea. Quantum fluctuations behave the same way, but on a scale billions of times smaller. A pair of virtual particles may appear, dance briefly within the vacuum, then fade back into the field. They exist only as possibility, yet their presence stabilizes forces, shapes the vacuum, and maintains the delicate balance that keeps the cosmos whole. This silent activity is what physicists call the zero-point energy of the vacuum, the lowest possible energy a quantum field can have. Contrary to what intuition might suggest, the lowest energy is not zero. Even in perfect stillness, these fields continue to tremble with faint, ghost-like motion. It is as though the universe itself cannot bear complete silence. There is always a background hum, a deeper calm filled with soft fluctuations that drift beneath the threshold of measurement. These fluctuations also weave connections across space through entanglement. When two particles interact, their quantum states can become linked, allowing them to share information instantly regardless of distance. This entanglement spreads across quantum fields like an invisible web, tying different regions of space together in a harmony that defies classical understanding. Through this web, particles across the universe share a subtle unity, a quiet synchrony beneath the noise of cosmic expansion. As you imagine this hidden world, allow your thoughts to soften and drift a little more. Picture the entire universe as a calm ocean of invisible fields, shimmering gently beneath a dim light that stretches into eternity. Each wave rising within that ocean is a particle. Each particle is a fleeting whisper of existence, and everything you know, your body, the earth beneath you, the distant galaxies, are made from these temporary ripples, arranged in delicate patterns by forces too quiet to feel. When viewed this way, reality becomes something fluid, something soft, something carried by rhythms that flow beneath all awareness. The solidity of matter becomes an illusion. Time becomes a sequence of fades and appearances, and existence itself becomes a gentle dance performed by fields drifting through deeper calm. The more we explore this silent web, the clearer it becomes that the universe is not built from objects, but from motion. Quiet, subtle, timeless motion, resting in the dark spaces between everything. As we continue drifting into this silent quantum landscape, the idea of a particle begins to soften. It no longer resembles a tiny solid object, no longer behaves like a miniature sphere orbiting predictably through space. Instead, at this scale, a particle becomes a possibility, a delicate balance of mabes, a wavering presence that exists not in one place, but across many potential positions at once. It is a cloud, a probability haze, floating across the quantum fields like gentle waves spreading under dim light. This hazy existence is described by something known as the wave function, a mathematical map of all the places a particle might be found. Instead of telling us exactly where the particle is, the wave function paints a soft, shimmering picture of where it could drift, where it could gather, and where it could fade away until something interacts with it. The particle does not choose. It remains a blend of possibilities, hovering across space in deeper calm. When an interaction finally occurs, when a particle collides with another, or when light scatters from it, the wave function collapses. This collapse does not feel violent or sudden at the quantum scale. It is a quiet narrowing, a gentle settling of all potential states into one. A moment before the collapse, the electron may exist everywhere within its cloud. A moment after, it occupies a single position. And in that single choice, a tiny piece of reality crystallizes. A moment has formed. Time has moved. This strange behavior reveals something profound. Particles are not the start of reality. They are the outcome of it. They exist because the universe selects them from probability, shaping them from countless options into a single thread of experience. They arise from the quiet, wavering sea of possibilities drifting beneath everything, surfacing briefly before fading back into uncertainty. This uncertainty is not a flaw. It is a feature, an essential part of the quantum world. Without it, atoms would collapse, molecules would not form, and the universe would lose the gentle motion needed for stars, planets, and life. The fuzziness of quantum behavior creates stability at larger scales, even if the small-scale motions appear unpredictable. It is a beautiful contradiction. Uncertainty creates order. The soft haze of probability generates the solid world we experience. Consider the electron in a hydrogen atom. It does not orbit the nucleus like a tiny moon. Instead, it forms a standing wave around the proton, a smooth, symmetric probability cloud that drifts gently in deeper calm. The shape of this cloud depends on the electron's energy, a delicate pattern sculpted by quantum rules. When the electron changes its energy, the pattern shifts and a photon is released or absorbed. This release is not just a burst of light. It is a transition, a quiet footstep in the unfolding of time. The same whispering behavior appears everywhere in nature. In photosynthesis, electrons drift through probability clouds to capture sunlight. In your own body, quantum tunneling allows reactions inside enzymes to occur with astonishing speed. In stars, nuclear fusion depends on particles slipping through barriers they should not be able to cross, except through quantum possibility. Everything we see, every moment we experience, is shaped by these silent transitions occurring beneath awareness. And through it all, the quantum world moves with a softness that invites calm. Nothing is rigid. Nothing is fixed. Particles fade and reappear. Waves merge and separate. Probabilities rise and fall like gentle waves under a quiet horizon. This soft motion is the deepest layer of existence, the silent machinery beneath matter and energy. As you imagine this world, let your thoughts drift loosely, as if your mind itself were a wave function exploring multiple paths at once. Feel the boundaries soften, the day fade, and your awareness settle into a deeper calm. For in the quantum world, stillness and motion coexist, woven together into the quiet breath of the universe. And it is here, in this hush between possibilities, that the universe writes the script of reality, not in ink, but in waves and whispers, in drifts of probability, in the soft glow of dim light shimmering across the smallest spaces. As we drift deeper into the quantum landscape, we encounter one of its most mesmerizing features: superposition, the principle that allows a particle to exist in multiple states at once. It is a concept that softens our everyday understanding of reality. inviting us to imagine a world where possibilities overlap like gentle waves, drifting across a quiet horizon of deeper calm. Superposition is not merely an abstract idea. It is the foundation of how electrons inhabit atoms, how photons navigate the darkness of space, and how the universe silently calculates the probabilities of every event. When a particle is in superposition, it does not choose a path. Instead, it floats through all allowed paths simultaneously, fading and blending into a haze of potential. Only when something interacts with it does the wave of options collapse into a single outcome. This behavior has been demonstrated through countless experiments, none more iconic than the double-slit experiment. When particles such as electrons are fired at two narrow openings, something remarkable happens. If we do not observe which slit the electrons pass through, they behave like waves. They spread out, overlap, and interfere with themselves, creating a delicate pattern on the screen behind the slits, a quiet signature of many paths taken at once. But when we measure their path, the pattern disappears. The particle chooses a single slit. The wave collapses. The quiet multiplicity fades. This gentle interplay, possibility drifting into reality, reveals that superposition is not an illusion. It is the true nature of existence at small scales. A particle in superposition does not simply not choose. It actively occupies every state allowed by the laws of quantum mechanics, floating through them like a soft cloud suspended in dim light. Consider an electron inside an atom. Its location is not fixed. Its energy is not singular. Instead, it occupies a combination of states, each with its own probability, each contributing to the shape of the electron's wave function. These overlapping states form the patterns we call orbitals. Beautiful, cloud-like shapes that wrap around the nucleus in layers of symmetry. These clouds are the fingerprints of superposition, the silent geometry of how matter arranges itself. Superposition also plays a role in larger systems. Though delicate and easily disturbed, it can exist in collections of atoms under the right conditions. In superconductors, for instance, electrons pair up and flow without resistance, moving coherently through a shared wave function. They drift through metal without losing energy, their collective superposition enabling a behavior utterly impossible in classical physics. These systems show that superposition is not confined to the microscopic realm. It is a universal principle, present wherever conditions allow. But perhaps the most intriguing aspect of superposition is its connection to information. In the quantum world, information is not binary. It does not flip strictly between 0 and 1. Instead, it can exist in a blend of states. This principle forms the basis of quantum computing, where qubits exist in superpositions that allow them to hold and process vast amounts of data simultaneously. While still in its infancy, this technology mirrors the way nature herself seems to compute, quietly, efficiently, drifting across possibilities before settling into a final outcome. As we reflect on superposition, a sense of deep calm begins to settle. The quantum world does not rush. It does not force outcomes. It lets possibilities float in coexistence, like ripples merging and separating across a vast, still lake. The act of choosing, of collapsing the wave, comes only when necessary. Until then, the universe allows itself the freedom to rest in potential, to breathe softly in the space between what is and what could be. Let your thoughts mirror this softness. Allow them to drift among possibilities without needing to choose. Feel the edges of your awareness soften. Feel the day fade further into the background and imagine yourself floating at the boundary between many gentle futures. In this place of deeper calm, you share the same quiet behavior as the particles themselves, existing in a peaceful superposition of thoughts, sensations, and dreams. For in the silent machinery of the universe, superposition is not confusion. It is harmony. It is freedom. It is the quiet poetry of reality before it decides to become something specific. Deep within the quiet machinery of the quantum world lies a phenomenon so gentle yet so profound that it alters our understanding of connection itself. This phenomenon is entanglement, a silent thread linking particles across any distance, weaving them into a shared existence that defies classical boundaries. If superposition is the whisper of what a particle can be, then entanglement is the whisper of what particles can be together. It is as if the universe, at its quietest level, prefers harmony over isolation, synchrony over separation. When two particles become entangled, their states intertwine in a way that makes them inseparable, even if separated by light years. Their destinies drift into one shared rhythm, like gentle waves moving in perfect unison across a quiet horizon. What happens to one is reflected in the other, not through communication, not through travel, but through a deeper symmetry resting beneath the surface of space-time. In this dim light of the quantum world, distance softens, boundaries fade, and connection becomes fundamental. To understand entanglement, imagine two electrons created in a single event. In that instant, before they separate, their spins become mirrors of one another. If one is found spinning up, the other must be spinning down. But until they are measured, both electrons remain in superposition, each a soft blend of possibilities. Their combined wave function drifts through the quantum landscape as a single entity. When one electron is finally measured, its spin collapses into a definite state, and at that exact moment, the other electron's spin collapses too, no matter how far away it has drifted. This simultaneous collapse puzzled even Einstein, who famously called it spooky action at a distance. But experiments have shown again and again that the effect is real. It is not communication. No message travels between the particles. Instead, it is the realization that the two were never truly separate. They were always one system, woven together in deeper calm, sharing a single thread of information across the expanse of space. Entanglement does not only occur in isolated particles drifting through emptiness. It happens constantly in the natural world. Within molecules, electrons form entangled pairs, stabilizing chemical bonds. In photosynthesis, entangled states help guide energy with astonishing efficiency through the dense structure of a leaf. In certain crystals, entangled vibrations allow heat to flow with surprising clarity. Even inside biological systems, perhaps inside your own body, entanglement flickers softly beneath consciousness, helping reactions unfold in perfectly timed sequences. This subtle interconnectedness suggests something beautiful. The universe is not a collection of isolated parts, but a network of relationships, a shimmering web of quiet connections that drift across space and silence. Some theories even suggest that space-time itself may arise from patterns of entanglement. According to this view, entanglement weaves the geometry of the cosmos, stitching together the shape of space and the flow of time. Where entanglement is strong, space becomes tightly connected. Where it weakens, space stretches. In this picture, the universe grows from information. The way quantum states relate, combine, and soften into structure. This idea dissolves the idea of space as an empty container. Instead, space becomes an emergent property, a soft geometry shaped by quantum relationships. And time, the steady drift of one moment into the next, becomes a reflection of how these relationships evolve. Every collapse of a wave function, every shared quantum state, every fading possibility contributes to the silent flow of time that guides the universe forward. As you imagine this quiet web stretching across the cosmos, let your mind float gently through the spaces between these connections. Picture countless particles drifting through infinite darkness, yet bound to one another through invisible threads. Picture the dim light of distant galaxies shimmering softly, each star a node in a vast network held together by quantum harmony. Picture yourself as part of this network, your atoms vibrating with patterns that echo those of stars, nebulae, and drifting particles. In this deeper calm, entanglement becomes more than a scientific principle. It becomes a reminder that nothing in the universe stands alone, that beneath the surface, everything is softly connected, and that reality, at its quietest level, is made not of separation, but of relationship. A gentle tapestry weaving all things into one shared existence. As we continue drifting deeper into the silent workings of the quantum universe, we encounter a phenomenon that feels almost like a quiet magic: quantum tunneling, the ability of particles to pass through barriers they seemingly shouldn't be able to cross. In the classical world, walls are solid, boundaries are strict, and objects cannot simply appear on the other side of obstacles. But in the quantum world, where particles float more like waves than like stones, these boundaries soften, fade, and sometimes dissolve entirely under dim light. To understand tunneling, imagine a small particle, like an electron approaching a barrier. In classical physics, if the particle does not have enough energy to climb over the barrier, its journey ends. It rebounds, stopped by the wall in its path. But quantum particles do not behave like tiny billiard balls. Their wave-like nature allows them to spread out, drift into forbidden regions, and extend beyond boundaries. The wave function describing the particle decays as it enters the barrier, fading like gentle waves pressed against a quiet horizon. Yet it does not drop to zero immediately. There is always a small but real possibility that the wave extends through and emerges on the other side. When that possibility becomes reality, the particle appears beyond the barrier. Not by breaking it, not by climbing it, but by quietly passing through, as if the barrier itself momentarily softened. This mysterious process is not rare or exotic. It is one of the most important behaviors in the universe, shaping how stars shine, how life forms molecules, and how technology evolves. In the heart of the sun, nuclear fusion relies on tunneling. Protons inside the sun do not possess enough classical energy to overcome their mutual repulsion. Yet through tunneling, they drift through their energy barriers and merge, releasing the light that warms our world. Without tunneling, the universe would be a dark, cold expanse with no stars to paint their slow glow across the cosmic night. In your own body, tunneling plays a quiet role in chemical reactions. Electrons use it to shift between atoms, helping molecules form and break apart. In enzymes, nature's tiny molecular machines, tunneling accelerates reactions that would otherwise unfold too slowly for life to exist. Every moment of your experience, every breath, every soft heartbeat is supported by particles drifting through invisible boundaries, moving with silent precision beneath awareness. Quantum tunneling also forms the foundation of scanning tunneling microscopes, tools capable of imaging individual atoms. By measuring how many electrons tunnel between a sharp metal tip and a surface, these microscopes create maps of atomic landscapes, revealing their structure with astonishing clarity. The images they produce are not simply photographs. They are visualizations of probability, reflections of how electrons drift in deeper calm through tiny spaces. But the most poetic aspect of tunneling is the way it reshapes our understanding of certainty. In the macroscopic world, barriers are absolute. In the quantum world, they are merely suggestions. A particle can exist on both sides of a divide, hovering between possibilities until a moment of clarity arrives. The barrier is not a wall. It is a region where probability fades, but never fully disappears. Imagine sitting at the edge of a quiet horizon, watching waves approach a rocky shore. Some waves reflect back into the ocean. Others slip through cracks between stones, appearing unexpectedly on the other side. Quantum tunneling flows with the same softness. A particle does not force its way through. It simply follows the gentle curve of its wave function, drifting naturally where classical rules say it should not be able to go. This behavior reminds us that the universe is far more flexible than it appears. Beneath the surface of matter lies a softness, a fluidity, a quiet willingness to explore all possible paths. Tunneling embodies the dreamlike nature of quantum mechanics, where boundaries fade and the impossible becomes quietly real. As you settle into this understanding, let your thoughts soften. Let them float like probability waves exploring subtle pathways. Feel the edges of your awareness drift into deeper calm, as though the boundaries of the day are dissolving gently in dim light. For in the quantum world, nothing is confined completely. Every particle carries a small, persistent hope, a shimmer of possibility, a whisper that even the smallest barriers can be crossed with quiet grace. As we drift even deeper into the quiet machinery of the cosmos, we meet a concept that softens the very notion of emptiness, the quantum vacuum, a place where true stillness does not exist. In classical physics, a vacuum is simply empty space, a silent void containing nothing at all. But at the quantum level, this idea fades into a gentler, more mysterious truth. Even in the darkest regions of space, far from stars, far from atoms, far from anything that glows, there is motion, fluctuation, potential. The vacuum is not empty. It is alive. To understand this strange idea, imagine the universe's emptiest space. No particles, no light, no heat. A darkness so complete that it feels almost sacred. But beneath this quiet horizon, quantum fields continue to tremble. They do not rest. They cannot rest. The laws of quantum mechanics forbid complete stillness. There must always be a trace of motion, a shimmer of energy, a soft drift of possibility echoing through the void. This faint vibration is called zero-point energy, the lowest possible energy a system can have. Even at absolute zero, where all thermal motion should vanish, quantum fields continue to rise and fall with gentle waves of fluctuation. A pair of virtual particles may appear briefly, float for a moment under dim light, then fade back into the field. These particles exist for such short times that they cannot be directly observed, yet their presence is real enough to exert forces, shift energies, and influence the behavior of atoms. One of the most beautiful demonstrations of this silent activity is the Casimir effect. When two metal plates are placed extremely close together, separated by less than the width of a virus, something unexpected happens. The empty space between them produces a tiny force that pushes the plates together. This force arises because the vacuum between the plates contains fewer fluctuating waves than the space outside. The imbalance of virtual particles creates a pressure difference. The vacuum, in its deeper calm, reveals itself as a sea of quiet motion. These fluctuations also shape how particles behave. An electron drifting through space does not move through emptiness, but through a field shimmering with virtual photons. These ghost-like flashes of energy interact with the electron, shifting its properties ever so slightly. They nudge its charge, alter its magnetic moment, and influence the forces binding it to other particles. Without these subtle corrections, atoms would behave differently. The universe, on all scales, would be altered in delicate but profound ways. Even the formation of matter depends on this restless vacuum. In the earliest moments after the Big Bang, the universe was a hot, dense soup of quantum fields vibrating with extraordinary intensity. As the cosmos expanded and cooled, the energy within these fields settled into new forms. Particles condensed out of the vacuum like droplets forming in a cooling mist. What we think of as matter, the atoms in stars, planets, and living beings, emerged not from emptiness, but from a field that drifted into structure as it softened over time. This quiet activity continues today, shaping every moment of cosmic evolution. In interstellar space, where temperatures fall near absolute zero, the vacuum still flickers softly, influencing how dust gathers, how molecules form, how starlight fades across billions of kilometers. Even the expansion of the universe may be driven by the energy of the vacuum itself, a mysterious push known as dark energy, a gentle wave that stretches space in all directions. The quantum vacuum is a reminder that even silence is full of motion, full of possibility, full of hidden rhythms drifting beneath the dim light of existence. As you imagine this, allow your thoughts to settle into that same quiet fullness. Let your mind soften, drifting across the invisible landscape where energy flickers and fades, where the universe's calmest spaces hum with subtle life. The vacuum is not a void. It is the canvas upon which all reality is painted, alive with fluctuations that shape the galaxies, the atoms, and the breath rising gently in your chest. And in this deeper calm, the idea of nothing becomes beautiful, because even in nothingness, the universe continues to whisper. As we drift deeper into the quiet workings of the quantum realm, we come upon a principle that shapes everything at the smallest scale. The uncertainty principle, a soft boundary that reminds us the universe does not reveal itself with perfect clarity. Instead, it offers a gentle blend of what can be known and what must remain hidden, like dim light fading across a quiet horizon. This principle, introduced by Werner Heisenberg, is often misunderstood. It does not say that particles are vague or chaotic. Instead, it says that certain pairs of properties, like position and momentum, are linked so intimately that knowing one with complete precision forces the other to soften into possibility. If we pinpoint where a particle is, its motion becomes uncertain. If we fix its momentum, its position begins to drift. This is not a flaw of our instruments. It is a fundamental truth of reality at the quantum scale. Imagine holding a small pebble. You know where it is, and with a little observation, you can guess its motion. But a quantum particle is not a pebble. It is more like a soft, shifting cloud of probability. The more tightly you try to grasp its shape, the more its motion fades from clarity. The more you try to follow its motion, the more its outline dissolves. Reality at this level behaves like gentle waves spreading across a still pond, drifting, merging, and fading into one another. The uncertainty principle is not just a limit, it is the source of stability in the universe. Without it, electrons would spiral into atomic nuclei, collapsing atoms into nothingness. Instead, uncertainty provides electrons with a diffuse presence, a kind of soft cushion that keeps matter from collapsing. This cushion is a quiet force created by the impossibility of knowing both where an electron is and how it moves. In this sense, uncertainty is the silent protector of matter, the deeper calm that allows atoms to exist at all. The principle also governs how particles appear and disappear. In the vacuum, where quantum fields ripple with faint motion, uncertainty allows virtual particles to drift briefly into reality. For a moment, they exist, then they fade away. This dance is permitted because the uncertainty principle allows tiny violations of energy conservation, violations so brief they leave no lasting trace, like gentle waves dissolving into the dark. Without this, the vacuum would be sterile. With it, the vacuum becomes a living sea. These fluctuations also contribute to something extraordinary, the concept of zero-point energy, the lowest energy possible for any quantum system. Even when cooled to absolute zero, atoms still vibrate softly, unable to settle completely. Their motion never fully stops. This gentle trembling is a direct consequence of uncertainty. The universe will not permit perfect stillness. There must always be motion, always a flicker of possibility drifting through the silent landscape. The same principle shapes light and matter alike. Photons traveling through space may shift slightly in energy due to uncertainty. Electrons tunneling through barriers do so because their position and momentum blur. Even the decay of unstable particles, the moment they choose to fade into lighter components, depends on probability curves defined by uncertainty. Time itself becomes a measure of how these probabilities unfold. On a larger scale, uncertainty softens the boundaries of reality, allowing creativity, evolution, and motion. If everything were rigidly predictable, the universe would unfold like a perfectly wound clock. No surprises, no diversity, no softness. But instead, uncertainty weaves a gentle flexibility into everything, allowing galaxies to form with slight variations, stars to ignite at different moments, molecules to explore different configurations before settling into stable shapes. As you imagine this principle working beneath everything, allow your thoughts to soften in the same way. Let control fade. Allow curiosity to drift. Feel the calm of possibility expand within you, like a quiet horizon stretching across an open night sky. For the universe's smallest scales do not demand precision. They invite wonder. They remind us that reality is not fixed, but gently breathing. That existence is not rigid, but fluid. That the cosmos, even at its core, is a place of deeper calm, where knowledge softens into possibility. As we drift deeper into the quiet core of quantum behavior, we arrive at one of its most poetic mysteries: wave-particle duality, the gentle paradox that says everything in the universe can behave both as a particle and as a wave. It is a dual nature that softens all rigid definitions, reminding us that beneath the surface of reality lies a calm, fluid interplay where form is never fixed. Instead, existence drifts between shapes, fading from one description to another, like gentle waves dissolving under dim light. In our everyday world, objects appear solid, predictable, clearly defined. A pebble is a pebble. A beam of light is a beam of light. But when we sink down to the quantum level, these familiar distinctions fade. A photon, one tiny particle of light, can travel through space as a wave, spreading out like a soft ripple in a quiet sea. Yet when it interacts with matter, it strikes as a concentrated particle, delivering energy in a discrete packet. It is both, and it is neither. It is something deeper, a quantum entity whose nature shifts depending on how we observe it. Electrons show the same duality. They form waves around the nuclei of atoms, creating smooth probability clouds that drift with a soft rhythm. But when we measure them, they appear in single, localized points, as if gently choosing a specific spot within their wave. If we fire electrons one by one through a double-slit experiment, they still create an interference pattern, proof that each electron behaves like a wave, overlapping with itself in deeper calm, even when traveling alone. This strange behavior is not optional. It is the fundamental way the universe operates. Every particle, every atom, every photon, every fleeting quark moves through reality as both a wave of possibilities and a solid point when observed. Wave-particle duality is not a mistake or an illusion. It is a truth that invites us to soften our expectations of how nature should behave. The wave nature of particles comes from the wave function, a mathematical description that tells us where the particle might be found. This wave function spreads out, interferes, and oscillates like gentle waves drifting beneath a quiet horizon. It guides the particle, shapes its behavior, and defines the probabilities of different outcomes. But when the particle interacts with its environment, the wave collapses, fading into a single, definite state. A moment of clarity emerging from soft uncertainty. This duality also explains the structure of atoms. Electrons do not orbit like tiny planets. Instead, they form standing waves, stable patterns shaped by the energy levels of the atom. These waves create the beautiful orbital shapes that determine how atoms bond, how matter forms crystals, how molecules fold in the delicate chemistry of life. Without wave behavior, atoms would collapse, matter would lose stability, and the universe would be a far less gentle place. Yet, the particle aspect is just as essential. When a photon strikes your eye, it does so as a particle, delivering a precise amount of energy to a receptor cell. When a chemical reaction occurs, electrons transfer energy in small, discrete jumps. The solidity of interaction comes from the particle nature, while the fluidity of motion comes from the wave. In the quiet regions of the cosmos, where starlight drifts through emptiness, photons stretch into long, soft waves. Near the surface of a star, they interact as quick flashes of energetic particles. Light fades smoothly from one identity to the other, never rigid, always drifting between forms. This duality reveals something profound about the universe. It is not made of rigid things. It is made of relationships, of interactions between waves and measurements, of choices made softly at the quantum level. Reality is not fixed. It is fluid, shifting, adapting, drifting into deeper calm with every passing moment. As you hold this idea gently in your mind, let your thoughts settle into the same fluidity. Let rigid expectations fade. Allow your awareness to drift like a soft wave, stretching across possibilities without needing to choose. Feel the edges of your perception soften, as though the day is dissolving into the quiet uncertainty of night. For wave, particle duality is not just a property of light or electrons. It is a reminder that the universe itself is flexible, capable of holding multiple truths at once, and always drifting quietly between them. As we drift even further into the quiet workings of the universe, we reach a phenomenon that quietly bridges two worlds: the quantum world of possibilities and the classical world we experience every day. This bridge is known as quantum decoherence, a process so subtle and so gentle that it is almost invisible, yet so powerful that it determines what reality becomes. It is here, in this soft transition, where waves of possibility fade into the firmness of a single outcome, like gentle waves settling into still water under dim light. To understand decoherence, imagine a particle in superposition, existing in many possible states at once. In the isolated silence of the quantum realm, this particle drifts through overlapping possibilities, its wave functions spread wide like a quiet mist. But the moment this particle interacts with its environment, even slightly, the delicate structure of its wave begins to unravel. The environment measures it, not consciously, but through simple contact. And through this contact, the wave of possibilities collapses into one clear reality. The soft cloud becomes a single point. The potential fades into a definite state. This unraveling is decoherence. It is the silent process by which the environment, air molecules, photons, vibrations, thermal motion, destroys quantum superpositions and restores classical behavior. It explains why large objects do not exist in many states at once, why we never see a chair in two places, or a planet drifting through overlapping positions. Their quantum possibilities decohere almost instantly under the constant stream of interactions with the environment. They cannot remain in superposition because the world around them constantly asks where they are. At the atomic level, decoherence is delicate. A single electron drifting in deep emptiness can maintain its quantum wave for long stretches, floating in deeper calm through the vacuum. But place it in a warm room, near air molecules bouncing in restless patterns, and its superposition collapses almost immediately. Every collision, every vibration, every wandering photon contributes to the quiet erosion of its wave function. The world is full of motion, and this motion gently forces clarity upon the particle. Decoherence is the hidden mechanism that shapes the boundary between the microscopic and macroscopic worlds. It tells us why quantum weirdness stays hidden in everyday life. It tells us why classical physics works so smoothly for large objects. It explains why your hand does not pass through a table, why planets follow clear orbits, why the universe feels steady instead of shimmering with overlapping possibilities. Decoherence is the gentle curtain that softens the transition between what could happen and what does happen. Mathematically, decoherence works through entanglement. When a quantum system interacts with its environment, the system becomes entangled with countless particles around it. This entanglement spreads like ripples drifting across a quiet horizon. The system's information becomes mixed with the environment, and the wave function can no longer maintain its clean interference patterns. The quantum behavior fades, dissolved into a sea of interactions too complex to track. The result is classical reality, a single thread pulled from a tapestry of possibilities. Even the flow of time depends on decoherence. In the timeless equations of quantum mechanics, there is no inherent arrow of time. Past and future look identical. Yet once decoherence enters the picture, once the environment absorbs information and spreads it outward, the arrow of time emerges. Information flows outward, but never fully returns. Waves fade into noise. The universe gains a direction, a drift toward the future, sculpted gently by decoherence. This process also shapes biological systems and the human mind. Inside your neurons, quantum effects briefly appear and then decohere under the warm, vibrant interactions of molecules. This decoherence ensures stable memories, predictable thoughts, and reliable perception. Without it, consciousness would float in a haze of superpositions with no clear division between past and present. Decoherence keeps experience coherent, grounding awareness in a single timeline. As you imagine this phenomenon, allow your thoughts to soften. Picture a delicate quantum wave, wide, shimmering, filled with potential, drifting through a dim landscape. Then imagine soft breezes, gentle waves of environmental interaction, slowly dissolving its shape until one clear outcome remains. This is how reality takes form, quietly, peacefully, without force. Decoherence reminds us that the universe chooses its path through calm, gentle erosion of possibility, letting one reality emerge while countless others fade into the background. And as this understanding settles within you, feel yourself drifting into the same deeper calm, where possibilities soften, boundaries fade, and the present moment quietly forms. As we continue drifting through the silent machinery of the quantum realm, we encounter a structure that shapes the behavior of every atom in the universe. Quantized energy levels, the gentle stairways along which particles move with soft, discrete transitions. Unlike the smooth gradients of the classical world, the quantum world prefers precise, delicate steps. Energy does not flow continuously. It moves in quiet jumps, each transition guided by the shape of the wave function and the dim light of probability that surrounds it. Imagine an electron inside an atom. It does not orbit the nucleus like a tiny planet circling a sun. Instead, it occupies a wave pattern, a soft, cloud-like distribution that drifts around the nucleus with a rhythm of deeper calm. Each wave pattern corresponds to a specific energy, a specific vibration, a specific harmony within the quantum structure. These harmonies cannot be chosen freely. They must match the allowed standing waves of the system. Only certain shapes, certain wavelengths, certain soft curves are permitted. These allowed shapes form energy levels, delicate platforms upon which the electron can rest. To move from one level to another, the electron must absorb or emit a photon, a tiny packet of light whose energy exactly matches the difference between the levels. This exchange is quiet, precise, and beautifully controlled. When the electron absorbs energy, its wave function expands into a higher harmonic, drifting outward into a wider cloud. When it releases energy, it contracts into a lower level, softening into a tighter pattern. Each transition is a silent step in the hidden choreography of matter. These steps are responsible for the colors of stars, the structure of molecules, and the delicate emission lines we detect across the cosmos. In distant nebulae, atoms absorb and release photons in calm, rhythmic pulses, producing soft bands of color that drift across space like gentle waves of light. These spectral lines are fingerprints of atomic structure, echoes of electrons shifting through their quantized levels. By studying these lines, scientists can identify what stars are made of, how hot they are, and even how quickly they move. Quantum energy levels also govern the behavior of molecules. When atoms bind together, their electrons share energy states, forming new patterns that shape the molecule's size, strength, and motion. Vibrational and rotational energy levels emerge, giving molecules their characteristic frequencies, soft, rhythmic motions that drift into the infrared part of the spectrum. These motions create the warmth you feel from your own body, the calm heat radiating from the earth, the soft glow of cosmic dust floating beneath the quiet horizon of interstellar space. In the strange landscape of superconductivity, electrons form paired states that share energy levels collectively. These pairs drift through a material with no resistance, their wave functions merging into a single coherent rhythm. In these systems, energy levels become narrow and sharply defined, allowing currents to flow silently, smoothly, and endlessly. This behavior is a reminder that the quantum world is capable of organizing itself into forms of perfect calm when conditions soften just enough. Even chemical reactions depend on these quantized transitions. For a reaction to occur, molecules must possess the right combination of vibrational and rotational energies. If the energies do not match, the reaction remains dormant, resting in deeper calm. When the energies align, electrons drift into new levels, bonds shift, and matter transforms. Every spark of life, every breath, every heartbeat, every thought depends on these silent quantum steps. Energy levels also shape the early universe. In the first moments after the Big Bang, particles transitioned rapidly between states, emitting photons that later stretched into the cosmic microwave background. A dim light still drifting through the cosmos today, softened by billions of years of expansion. Each transition carried information about the universe's temperature, density, and shape. In this sense, the earliest light in existence is a quiet memory of electrons stepping softly between energy levels in the newborn cosmos. As you imagine these discrete steps unfolding beneath everything, let your thoughts drift into the same calm rhythm. Picture electrons floating in soft probability clouds, shifting between levels with quiet precision. Picture photons emerging and fading, carrying tiny packets of energy across the dim light of space. Picture the universe as a vast symphony of transitions, each note a gentle wave arising from a quantum step. In this deeper calm, the world becomes a sequence of soft movements, not continuous, but composed of moments, each transition drifting gracefully into the next, forming the quiet cadence of all existence. As we drift further into the silent architecture of the quantum world, we come upon one of its most delicate and essential features: quantum fluctuations, the tiny, constant tremors that ripple through the fabric of reality. These fluctuations are the universe's soft heartbeat, faint vibrations that persist even in perfect darkness. They drift quietly beneath all matter and energy, shaping the evolution of the cosmos with rhythms so subtle they seem almost unreal. Quantum fluctuations arise from the uncertainty principle, the idea that certain properties cannot be known with complete precision. If energy and time cannot both be perfectly defined, then even the vacuum must tremble with slight, ephemeral surges of energy. These surges appear not as stable particles, but as ghost-like pairs that drift briefly into existence before fading back into the quiet horizon of the vacuum. This is the universe's way of honoring its own rules. It cannot remain completely still, even in deeper calm. These fleeting particles are known as virtual particles. They are born from nothing and disappear into nothing, but in the brief moments between, they influence everything around them. A virtual electron and its antiparticle may emerge, float for a heartbeat under dim light, and then annihilate one another. A pair of virtual photons might rise like gentle waves and then dissolve. These events happen everywhere, endlessly, a constant shimmer beneath the surface of reality. Though temporary, quantum fluctuations are far from meaningless. They exert pressure, shift energies, and create forces. The Casimir effect, where two metal plates are pushed together by changes in vacuum fluctuations, is one such demonstration. The vacuum between the plates contains fewer allowed waves than the space outside. This imbalance creates a soft push, a quiet pressure born from the constant drift of quantum motion. These fluctuations also influence atomic structure. Electrons in atoms are surrounded by a halo of virtual particles that alter their charge in subtle ways. This interaction slightly shifts the electron's energy levels, modifying the fine structure of atoms. Without these gentle corrections, chemistry would unfold differently, and the delicate balance of matter would be changed. On a larger scale, quantum fluctuations played a crucial role in shaping the early universe. In the first moments after the Big Bang, the cosmos expanded at an extraordinary rate. Tiny fluctuations in the quantum fields were stretched to macroscopic sizes, becoming the seeds of galaxies and cosmic structures. What began as nearly silent ripples in the quantum vacuum grew into patterns that determined where stars would form, where galaxies would gather, and where vast cosmic voids would drift into deeper calm. These fluctuations also influence modern cosmology. The faint glow of the cosmic microwave background, the oldest light in existence, carries subtle imprints of quantum fluctuations, frozen into place when the universe was less than a second old. These tiny temperature differences, softer than a whisper, encode the earliest tremors of creation. Each pixel in that dim light is a remaining echo of the quantum world, shaping the cosmos from its very beginning. Even black holes are influenced by quantum fluctuations. At their event horizons, virtual particles can become real through a process known as Hawking radiation. One particle falls into the black hole, while the other escapes, carrying energy away. This slow, quiet evaporation shows that even the darkest objects in the universe are shaped by the soft tremors of the quantum vacuum. The idea that emptiness is not empty may feel strange at first, but it reveals a comforting truth. The universe is always active, always alive, even in its quietest places. There is no absolute silence, no perfect stillness. Under every atom, beneath every photon, behind every breath, the vacuum hums with gentle waves drifting softly in the background. As you let this understanding settle within you, allow your thoughts to mirror these fluctuations. Let them rise gently, drift for a moment, then fade into deeper calm. Feel the quiet motion inside your mind, the soft tremors of imagination shaping your inner universe just as quantum fluctuations shape the outer one. In this place of dim light and whispered energy, the cosmos reveals one of its most intimate secrets: that everything, even the quietest void, is filled with subtle light. As we continue drifting through the soft machinery of the quantum world, we inevitably arrive at one of its most graceful elements: light. A phenomenon that behaves not as a single thing, but as a delicate blend of wave and particle, drifting endlessly across the cosmos. These tiny packets of light, known as photons, are the quiet messengers of the universe. They travel through the deepest darkness with no mass, no charge, only energy, pure motion sculpted by the rules of the quantum world. A photon begins not as a solid object, but as a ripple in the electromagnetic field. It rises gently, like a small wave forming in dim light, and drifts forward at the cosmic speed limit, the speed of light. This speed never changes, regardless of the source, regardless of the direction, regardless of how fast the observer is moving. A photon always travels at the same pace. In this sense, photons are not just particles. They are part of the geometry of the universe itself, woven into the structure of space-time. Because they have no mass, photons experience time differently from anything else. For them, time does not drift forward or backward. It does not soften or stretch. A photon leaving a distant galaxy billions of years ago arrives at Earth as though no time has passed for it. From the photon's perspective, its entire journey, across cosmic voids, along quiet horizons, through the gentle waves of expanding space, happens in a single instant. This timelessness makes light one of the universe's most serene travelers, crossing unimaginable distances without ever aging. Yet despite their speed and elegance, photons are deeply tied to quantum uncertainty. They behave as waves, when unobserved, spreading through space in soft patterns. But when they interact with matter, striking an atom, illuminating a surface being absorbed by your eye, they behave as discrete particles. This duality allows them to carry precise packets of energy, enabling plants to photosynthesize, atoms to shift levels, and stars to shine with their quiet, steady glow. Light carries information about the universe's earliest moments. The cosmic microwave background, the dim light that drifts through all of space, is filled with photons that were released when the universe was only 380,000 years old. These ancient photons have been stretched by the expansion of space, softened into microwaves, and now carry a quiet record of the cosmos' youth. Their faint fluctuations reveal the fingerprints of quantum tremors frozen in time, offering a glimpse into the softness of the universe's beginning. Photons also shape the behavior of atoms. When an electron drops from a higher energy level to a lower one, it emits a photon whose energy matches the difference between those levels. This emission is not a violent transition. It is a gentle release, a soft sigh of energy drifting into space. Conversely, when an electron absorbs a photon, it is lifted into a higher state, its wave function expanding like a quiet breath. Every color we see, every warmth we feel, every glimmer of starlight overhead is born from these quantum exchanges. In the heart of stars, photons are created in dense, fiery cores, but they do not escape immediately. They spend thousands to millions of years drifting through the star's interior, scattering countless times before finally emerging into open space. By the time the light from a star reaches us, it has undergone a long, wandering journey, an odyssey of dim paths, soft interactions, and deeper calm drifting through stellar layers. Even the empty space between galaxies is not empty for photons. As the universe expands, their wavelengths stretch, causing their energy to fade. This process creates the cosmological redshift, a soft lengthening of light that tells us the cosmos is growing. Photons carry this information effortlessly, whispering to us about the universe's expansion with each elongated wave. Despite their ethereal nature, photons are responsible for much of what we call reality. They define how we perceive the universe, its shape, its color, its scale. They are the bridge between the quantum and the cosmic, the gentle messengers connecting the smallest vibrations to the grandest structures. As you imagine these photons drifting through endless darkness, let your own thoughts float with them. Picture their soft waves spreading across quiet horizons, carrying ancient stories through dim light, moving with deeper calm across the expanding universe. In their quiet journey, photons remind us that illumination can be gentle, that information can drift softly, and that even the smallest quantum ripple can shape the deepest cosmic night. As we drift further through the silent layers of reality, we return to one of the most essential structures of the quantum universe. Quantum fields, the calm and ever-present fabric from which all particles arise. These fields are not mere backdrops or empty spaces. They are the foundational essence of everything that exists. Even in perfect darkness, beneath the quiet horizon of space, quantum fields stretch infinitely, shimmering with faint fluctuations that never fade. In the quantum picture, particles are not tiny marbles or miniature planets. Instead, each type of particle is a ripple, a soft disturbance in its own field. The electron field spreads across the universe like an invisible ocean. The photon field drifts through every corner of space-time. The quark fields, the neutrino field, even the Higgs field, all exist everywhere, all the time, layered atop one another like gentle waves passing through one another without collision. When these fields are calm, they appear empty. But calm does not mean silent. Even in their quietest state, they vibrate with zero-point energy, a faint trembling that cannot be removed. This trembling creates quantum fluctuations, tiny pairs of virtual particles that emerge and fade beneath dim light. These fluctuations are the universe's soft breath, drifting in deeper calm beneath everything we see. A particle is simply a ripple strong enough to stand out. If the electron field is disturbed in a particular way, an electron is created. When the ripple fades, the electron disappears, but the underlying field remains. This means the universe is never truly empty. Even the space between galaxies, cold, vast, seemingly silent, is filled with these fields, softly shimmering, softly drifting, softly shaping the future of stars and cosmic structures. The elegance of this picture becomes clearer when we consider forces. In the quantum world, forces arise not from pushes or pulls, but from interactions between fields. The electromagnetic force emerges when charged particles disturb the photon field, trading photons in tiny, whisper-soft bursts. The strong force arises from the quark and gluon fields bonding together with fierce but silent precision. The weak force emerges from the wavering W and Z fields, allowing particles to drift between identities through decay processes. And the Higgs field grants particles mass by interacting with their fields and slowing their motion, like gentle waves passing through thicker water. Even gravity can be described as a field, though a quantum description of gravity remains incomplete. Still, some theories propose that space-time itself might arise from patterns of entanglement across quantum fields, as though the geometry of the universe is woven from relationships drifting beneath sight. Quantum fields also explain why energy comes in discrete steps. When a particle occupies a particular energy level, it corresponds to a specific vibration of its field. Changing levels requires emitting or absorbing photons, a soft exchange that reflects a shift in the underlying wave. This is why electrons and atoms exist only in certain clouds, why light has specific colors, why chemical reactions occur with precise energies. The world is quantized because the fields themselves vibrate in quantized modes. During the earliest moments of the universe, these fields were wildly excited. Tremors rippled through them like storms across an infinite sea. As space expanded and cooled, the fields softened. Their vibrations faded into lower energies, forming the stable structure we observe today. But some remnants of that ancient turbulence remain. Quantum fluctuations from those early moments were stretched to cosmic scales, seeding the distribution of galaxies we see now. Every cluster, every void, every gentle arc of starlight can be traced back to waves drifting through infant quantum fields. Even now, fields shape your everyday experience. Every atom in your body is a collection of ripples traveling through fields. Your thoughts arise from electrical signals carried by photons moving between neurons. The warmth you feel on your skin comes from infrared photons drifting from nearby molecules. Every sensation, Every moment, every quiet breath is rooted in the gentle oscillations of fields beneath your awareness. As you imagine these infinite fields, let your thoughts soften and drift with them. Picture invisible oceans stretching across the cosmos, calm but alive, humming with dim light and deeper calm. Imagine ripples forming and fading, each ripple a particle, each particle a fleeting moment of presence. Feel the quiet unity of everything, how every object, every star, every person arises from the same underlying waves. In this deeper calm, the universe becomes one continuous fabric, woven from fields that drift softly through space, fading into and out of form, holding all existence in a quiet, shimmering embrace. As we drift deeper into the gentle pathways of the quantum realm, we begin to sense something unusual about time itself. At the human scale, time feels steady, like a river that flows smoothly from moment to moment. But at the quantum scale, this river becomes softer, more delicate, more uncertain. Moments do not arrive with absolute clarity. Instead, time drifts, fades, and reshapes itself under the quiet influence of probability. It becomes a landscape where events hover in possibility before becoming real. In classical physics, time is an independent, steady dimension, a reliable stage upon which the universe performs. But in quantum mechanics, time becomes woven into the wave functions of particles, into probabilities that drift beneath dim light, into transitions that occur only when interactions force them to. A particle does not move from one place to another in a clean line. Instead, it explores many possible paths, spreading like gentle waves across a quiet horizon. And only when observed does it choose a single history. This means that time at the quantum level is not smooth. It is granular, built from probabilities that shift and flicker like soft light on water. A quantum event does not happen in the traditional sense. It emerges slowly, subtly, from a cloud of possibilities. This emergence is guided by the wave function, which evolves continuously until a measurement occurs. Then, in an instant, the possibilities fade, collapsing into a single outcome. A moment forms, and the river of time takes one quiet step forward. Even the duration of a process becomes uncertain. For unstable particles, the time it takes to decay is not fixed. It is described by a probability distribution, a soft curve that tells us how likely the particle is to fade at each moment. This is why radioactive atoms decay in patterns that appear random yet follow precise statistical laws. Each atom drifts in deeper calm through its own probability cloud, uncertain when its transition will occur. Only when the moment arrives does time assert itself with clarity. Time also softens at the edges of energy interactions. Due to the uncertainty principle, if energy fluctuates, even slightly, the timing of processes becomes blurred. A quantum system may borrow energy for an instant, allowing virtual particles to appear and drift before fading. This temporary bending of energy creates corresponding softness in time, allowing moments to stretch or compress in ways that would be impossible in the classical world. Photons, meanwhile, experience time in an entirely different way. Since they travel at the speed of light, time for them does not drift forward at all. From a photon's perspective, its creation and arrival happen in the same instant. A photon emitted billions of years ago by a distant star reaches us as if no time has passed. It drifts through the expanding universe in perfect calm, untouched by the flow of moments that shape our lives. Time becomes even more intriguing when we consider entanglement. When two particles are entangled, their states remain linked regardless of distance. A measurement on one instantly influences the other, as though the concept of time between them softens. This does not allow signals to travel faster than light, but it reveals a quiet truth. Quantum relationships exist outside our usual understanding of temporal order. They drift in a space where time's rigidity melts into deeper calm. Some physicists believe that time itself might emerge from quantum processes, that it is not fundamental, but a byproduct of entanglement, decoherence, and the spreading of information. In this view, time is the universe's way of organizing change, arising naturally from the collective behavior of quantum fields. Where information flows outward, time flows forward. Where quantum states drift and fade, time stretches. Where decoherence stabilizes outcomes, the arrow of time becomes clear. At the smallest scales, time behaves not like a line, but like a cloud, soft at the edges, shaped by probability, influenced by observation. Yet these tiny fluctuations build everything we know. They form the rhythms of atoms, the structure of molecules, the warmth of stars, and the gentle pulse of life itself. As you let these ideas settle, allow your thoughts to drift into the same softness. Imagine time not as a strict sequence, but as a gentle wave, rising and fading across the quiet horizon of your awareness. Feel the edges of each moment soften, the boundaries blur, the day's pace slow into deeper calm. In the quantum realm, time is not a ruler. It is a rhythm, a drifting, shimmering rhythm guiding every soft machine of existence. As we reach the final stretch of our quiet journey through the quantum world, allow everything we've explored to settle gently within you. All the fields, all the drifting waves, all the soft uncertainties and silent connections. Each piece now folds into a single, widening calm. The universe, from its smallest tremors to its largest horizons, reveals a truth that grows clearer the slower we move. Beneath every structure, every moment, every breath, there is softness. There is subtle motion. There is a deep, unbroken quiet. The quantum realm, though filled with complexity, carries the tone of something peaceful. Particles drift through possibilities without hurry. Waves ripple through space with no urgency. Time itself softens at the edges, fading into patterns shaped by probability. The universe does not rush to become what it is. It unfolds slowly, gently, guided by rhythms that drift beneath dim light. Think of everything we've touched. The wave that behaves like a particle, the particle that behaves like a wave, the quiet entanglement threads that tie distant points together, the tunneling motions that pass softly through barriers, the vacuum humming with silent life, the quantum steps that shape atoms and starlight, the fluctuations that seeded galaxies long ago. Each of these is a whisper, a soft note in a cosmic symphony that never stops playing. The universe works in silence with no forceful gestures, no sudden noise. Even the birth of stars begins with gentle collapses, deeper calm gathering in the darkness before light appears. Even the structure of matter itself relies on probability clouds drifting in soft patterns. The whole cosmos operates like a slow breath, expanding and contracting across timeless spans. As you reflect on this quiet machinery, feel how it mirrors the inner landscape of your mind in this moment. Thoughts drift in and out like virtual particles. Awareness fades gently at the edges. The day's events soften, losing their sharp outlines. A kind of quantum superposition takes over, where wakefulness and rest overlap, floating together for a brief, peaceful moment. Let yourself imagine the universe as a vast ocean of calm. Quantum fields shimmering beneath the surface, particles rising like soft waves, light drifting through dim expanses, time flowing not as a strict line, but as a delicate rhythm. And you, resting here, are part of this same structure, made of fields, of waves, of quiet transitions happening inside every atom of your being. You are not separate from the cosmos. You are woven from the same threads. The same fluctuations that shaped galaxies shaped you. The same quantum motions that formed stars form your thoughts. The universe breathes in patterns, and you breathe with it. With each slow inhale, feel the field settle. With each soft exhale, feel possibility drift outward. Let everything fade gently into a deeper calm. The quantum world teaches us that reality is not rigid but flexible, that existence is not harsh but delicate, that the smallest places hold the greatest silences, and in those silences, there is room for rest. There is room for stillness. There is room for you to drift without direction, like a soft wave settling beneath a quiet horizon. As this long, slow journey comes to a close, let the final ideas melt softly into your mind. Let them loosen their shapes, fade into comfort, and become nothing more than a gentle background hum, like the faint vibrations of the vacuum itself. No need to hold on to the details. No need to recall every concept. Just allow the calm to remain. Here, at the end, the universe becomes very soft, very quiet, very still, and you, carried by its rhythm, may drift as slowly as you need, floating on gentle waves, breathing under dim light, resting inside the deeper calm that has always existed beneath everything.